Good afternoon, class. This is Mr. Coy. So this is, in case you can't see at the bottom, this is page 7 in your large packet. So I want you to first work on this on your own and then go over it. So just some key pointers. Do recall, this is a velocity graph, so treat it accordingly. Remember, if it's asking how fast, what does that mean if we say how fast? If you said speed or velocity, you're absolutely correct, so do not overthink the first couple of questions. Also, I know we haven't really gone over formulas very much, so don't worry too much about those asking for the formula. Although for this one, think, how are you going to find acceleration with a graph? That formula. Alright, so hopefully you attempted this on your own first. So first things first, we gotta look at how fast and in what direction is the car moving at 3 seconds. So this is a simply find the 3-second mark on your graph. Go up, find it on the graph there, and mark it. I would say that's about 28 meters per second. Alright, so if you had trouble with that, go ahead, pause, try the next one. So again, we're just going over to t equals 5, going up and then across with it. I'm going to say that's maybe 51 meters per second. Alright, and I'm going to clear these answers so we have more room. Alright, and then same thing for 8. 8, we have a nice line, but we can see, oh look, we have a straight line. Our speed here is constant, and it's at 60 meters per second. Alright, so considering the formula for acceleration, how could you use this graph to find? I think they're talking about this equation. So we know here v naught, the original v, is 0, so we can get rid of that essentially. Or another way to think of it is v minus v naught over time. I quickly subtracted that from both sides and divided this by t, and we have this equals a. Hopefully this looks a little familiar to you. This should look like a change in v. Oops, that should be a v. Change in v over time, also known as the change in y over the change in x, which is your rise over run. So really, if you manipulate the formula, you essentially just get the formula for slope, and that's really all it's talking about. So how could you find it? Find the slope. So that brings us to actually finding the slope. So at 2 seconds. So remember, you need 2 points. You can pick any 2 points, but you do need 2. Of course, we know our first point is going to be 2 and 20. And we can see, aha, this is a really easy point here at 0, 0. So our second point is 0, 0. Because we can still use it because it's still on that line. Has the same slope. So it's going to be your final y minus your initial y over your final x minus your initial x, which would just give us 20 over 2, which will simplify to 10 and keep your units meters per second cubed. So remember, there's a seconds down here, and this is meters per second. Alright, then you gotta go to the next one, 8. Hopefully, you can see from this that this is a flat line. And we know that a flat line, if we go here and we try to find the difference between them, there is no difference, which gives us a 0 on the top. Doesn't matter how big our change in seconds is on the bottom, it's still going to be 0 meters per second squared. Remember, do keep the units. So our acceleration, if we have a velocity graph, we find acceleration from the slope. Alright, moving on. If we now do displacement, Remember, displacement is the area under the curve. So essentially from 6 to 10 is this area in here. So it's a big rectangle, so you need to find the base times the height. So we can go, the base is from 6 to 10, so our base is 4 seconds. Our height goes all the way up here to 60 meters per second. You're going to be able to cross out your seconds. And then it's 40 times 60, or think of it as 40 times 6, which should give us 24, and then bring our 0 back in, meters, and that is, remember, for 7. Alright, then it splits it up, and then it says, what about from 0 to 6? So it's still finding the area under the curve, but remember, this is a triangle, so the formula is now 1/2 base times height. So to get that, it's still, our base is now from 0 to 6, so that gives us 6 seconds for our base, and our height, it still gets up to 60, and that's where the half comes in. That's meters, 60 meters per second. You can cross out your seconds. We now 6 divided by 2 gives us 3, and 3 times 60 gives us 6 times 3 is 18, so 180 meters for 8. So if you added those up, you get 240 plus 180 gives you the total displacement traveled, which would be 420 meters. Okay, so don't worry too much about 9, but I'm going to manipulate this equation to hopefully help show you what I mean when I do the answer. So first you want to get things you know alone. So v naught, the original velocity, is going to be 0, so this essentially goes away. We're left with the 1/2 acceleration times t squared, and we know these, but we actually don't know two variables. We don't know x, its final position, and we don't know x naught, its initial position. So what we could find from this, because we know all of these, we know how much time it took, 6 seconds while accelerating, and then 0 seconds while, or 0 acceleration from 6 to 10. We, however, do not know where it started and where it ended. So we could find the displacement, we can never find the original position because we have two unknowns. That's what 9 is trying to get at. So you can find displacement, how far it traveled, but you don't know where it ended, you don't know where it started, you can't be sure of either one. If the problem told you either one, then you could find it, because then you would be able to answer one of those. But otherwise, you can only find the displacement with a velocity graph, not the position, which is why I always say displacement and not position, and while I'll sometimes say they can be used interchangeably, but not always. This is one of those cases. It is only displacement here because we do not know its final position or initial position. Alright, so the next thing it says is make both an x and t graph and an acceleration and t graph based on this graph. So I'm not looking for super exact values, but I do want you to have a basic idea. So right here, after 6 seconds, we can see that we have gone 180 meters. So at the 6-second mark, your graph should go up to 180. But remember, we are accelerating here. We have a positive acceleration. So that's going to give us that curved smiley face kind of line. Then up here we see velocity is constant, which remember gives us a straight line, and that it's going to end at 10 seconds up at 240. Now this graph is not to scale at all, but I just want you to have a general idea of what it would look like. So you're going to have a curved line and then a straight line coming off of it. That is what your x and t graph should look like. And it should end, it's 10 equals 240, because that was our total displacement for that. Excuse me, that's not right at all. So your total displacement is 480 after both of these. So your change here should be 240, but your overall top distance should be 480, which remember is we added those, so total it went 400 and, oops, added wrong, I'm very sorry, 420. Went 420 meters total. So your top line, let me redraw that for you really quick. So your top